I'll be highlighting the important tables for you. The important tables from the point of view of thermodynamics are table A4 to A7. They are the most important tables, very frequently used. So I'll be focusing on these tables. And once you understand the working of these tables, you should be able to utilize the tables A11 to A13, which are the tables that deal with refrigerant R134A. Other than that table, the table which is very frequently used is the ideal gas properties of air table, and the table A2, A2B and A2C when you have to calculate the CPs and CVs with regards to temperature. So these are the important tables. This session I'll focus on the saturated water temperature table, saturated water pressure table, superheated water table, and the compressed liquid table. So table A4 to A7, these are the essential tables I'll be focusing on in this session. The tables A4 to A5, they are basically tables under temperature and pressure. The difference is that table A4 is essentially used where the first column is of temperature, A4, and the second column is of saturation pressure. The table A5 essentially is exactly the opposite where the first column is of pressure, table A5, and the second column is of saturation temperature. And in these tables, if you look at the subscripts that are being used for specific volume, internal energy, enthalpy, and entropy, the subscript F is used for saturated liquid, the subscript G is used for saturated vapor, and wherever you have FG, VFG, HFG or UFG or uh, SFG, it is basically the difference between the saturated vapor state and saturated liquid state. So this difference is also tabulated for you. Now, moving on towards the understanding of table, as I had mentioned in the saturation pressure table, saturation temperature table, if you know that your system is saturated liquid at 90 degrees centigrade, essentially, if you want to find out the pressure corresponding to 90 degrees centigrade would be your saturation pressure, and this pressure would be constant if you are having the constant pressure line like this shown in the diagram. All the properties are relevant to this temperature, and for this state, saturated liquid state, are represented by VF, UF, HF, and SF. So if you want to find out the VFG, you have to take the difference between VG, the saturated vapor state, and the saturated liquid state. Similarly, UFG and HFG, they are given to you in the table. HFG is essentially the property that represents the amount of heat required to evaporate saturated liquid to saturated vapor per unit mass. This is the latent heat of vaporization. For saturation properties of water under pressure, table A5, again, as I had mentioned, the first column is for pressure, the second column is for the saturation temperature, and the rest of the columns, they are essentially the same. The specific volume, internal energy, enthalpy, and entropy tables. So if you have saturated vapor at 350 kilopascal and you want to find out the rest of the properties, for example, if you want to find out the temperature of your system, you'll directly go to 350 kilopascal and read the temperature corresponding to it. This would be the temperature for your system. There's the constant temperature line, and the temperature corresponding to your state would essentially be 138.86 degrees centigrade. You can find out the saturated vapor volume, specific volume, using the corresponding VG value. Now, when you are in the mixed state, that when you are on any point on this line, when you are lying on this line, over here, here, you have a mixture of saturated vapor and saturated liquid within the dome. In order to quantify the position on the line, you define the value of quality, which is defined as X. Quality is nothing but it is the mass of vapor, which is mg, divided by the total mass of the system. And you should remember that total mass is the mass of liquid plus mass of vapor, which is mf plus mg. Furthermore, if I am at this line, which is a saturated liquid state, my x value would essentially be 0 since my mg is essentially 0. And if I am at this line, saturated vapor line, my x value would be 1, which is the place where mg is equal to the total mass of the system. So the value as I move from saturated liquid to saturated vapor, the x value is essentially increasing from 0 to 1. The important thing is how to find the average value of the mixture. If you have saturated vapor and saturated liquid amounts varying together in a system, you would represent the system as a mixture where you'll express the properties of mixture as the average values which are determined from Vg and Vf values. So Vg and Vf values, they contribute towards the average value of the system. Average values, I mean, these values could vary from specific volume, internal energy, enthalpy, and entropy. So um, I'll not go into the derivation of it. The simple expression that we have for the average value is essentially V average is equal to 1 minus XVF plus XVG. This is further simplified if you could express VFG is equals to VG minus VF. If you use this expression, you can simplify the relationship, and any average value of your mixture could be expressed in terms of Vf plus X VFG. Now, if you have a specific pressure, Vf would be constant, Vfg would be constant. Only the change in X value would help you determine the relevant average specific volume for this matter. Or if you use HF and HFG, it would give you the average enthalpy value. Or if you're using internal energy and UF and UFG, it would give you the average internal energy value. So any value, average value, or any average property of a system can be expressed in terms of Vf, Vfg, and X that determines the amount of saturated vapor and saturated liquid in the system. Moving on towards the superheated vapor region, how to identify the superheated vapor region? There are basically five characteristics that define the region. If you have pressure, specific volume plot, and a constant temperature line, this is the constant temperature line in a PV plot, and this is a constant pressure line in a PV plot. Now, in a PV plot, this temperature is essentially the saturation temperature, and this pressure is essentially the saturation pressure, and this temperature essentially is the saturation temperature. So if you have pressures less than saturation pressure, so if you have pressures, any pressures which are less than this saturation pressure for a constant temperature, you are this line is in the superheated region. Similarly, if you have temperatures greater than T saturation for a constant pressure, so if your temperatures are greater than T saturation for a constant pressure line, you are essentially in the superheated region. Similarly, if your properties such as specific volume, internal energy, and enthalpy are greater than Vg, Ug, and Hg for a specific pressure or temperature, you are essentially in the superheated region. These five characteristics helps you identify the region of your system. Once you have identified the region of your system, you'll go to table A6, which is the superheated table. And the superheated table is basically you'll have to identify the pressures that you are dealing with. For example, if you have a system in which your pressure is 0.5 megapascal, your saturation temperature is 1115 and your system temperature is 250 degrees centigrade, you are essentially having the temperature greater than T saturation. T is greater than T saturation, so you are in the superheated region. And for this, if you want to find out the properties, for instance, if you find out the specific volume V or V average, sorry, if you want to find out the specific volume for this condition, you will go to the pressure column having 0.5 megapascal pressure, and you will go to the temperature column to read the temperature of your system, which is 250 degrees centigrade. The value corresponding to these two would give you the specific volume. In every superheated table, the first row is for the saturation properties. These properties are basically properties for saturated vapor state. That means these are the properties for this state they are given. Just next to the pressure column, there is a temperature written, which is the temperature of the saturation temperature for the pressure that you're dealing with. So this is the temperature of saturation for that pressure, and the saturation row contains the properties corresponding to saturated vapor state. Now, when you are dealing with compressed liquids, you essentially have to deal with table A7. At times, you might not have the data relevant or required for table A7 given to you. In such a case, there is an facility to use the approximated values. So if you have the properties given to you exactly, for example, if your system is at 80 degrees centigrade, 5 megapascal, you are in compressed liquid region. If the compressed liquid table could give you the properties, good enough. If not, you'll have to approximate the properties by using the approximation. For instance, I take y as a symbol for all the properties. U, V, H, S, all the properties are represented by the symbol y. So any property can be approximated by taking the saturated liquid value of that property at the given saturation temperature. So if your system is at 80 degrees centigrade, you will consider saturation temperature of 80 degrees centigrade, where you have saturation temperature of 80 degrees centigrade, and you would read the VF property, UF property, HF or SF property as an approximation for this temperature. Now, let us have a look at few of the examples to help us better understand the use of the tables. It says a rigid tank contains 50 kg of saturated liquid water at 90 degrees centigrade. You have to determine the pressure in the tank and the volume of the tank. First thing, saturated liquid, 90 degrees centigrade. So if you want to determine the pressure, it would be the saturation pressure corresponding to 90 degrees centigrade. This is your pressure for the system. And if you want to determine the volume of the tank, you need to have the specific volume. Since it's saturated liquid, this is a specific volume. Specific volume is per unit mass. You can multiply it by the given mass and it would give you the volume of the tank. So Vf at 90 degrees multiplied by the mass would give you the volume of your tank for this state. Now it further says a mass of 200 grams having saturated liquid water as the initial state is completely vaporized. That means it is converted into saturated vapor at constant pressure of 100 kilopascal. So you are in the isothermal region or isothermal line. So this constant temperature line is there, and you have converted the system from state 1 to state 2. You have to determine the volume change and the amount of energy transferred to water. So in order to calculate the volume change for 100 kilopascal, you will have to find out Vf, Vg. The difference of the two would give you change in specific volume. You will multiply it by the corresponding mass, and this would give you the volume change. Similarly, HFG is given to you. Just multiply it with the mass, and it would give you the corresponding change in energy that is being transferred to the system as the system moves from state 1 to state 2. Then comes the problem where you have mixed region. It says a rigid tank contains 10 kg of water at 90 degrees centigrade. It further says if 8 kg of the water is in the liquid form, that means MF is 8 kgs and the rest is in the vapor form. So Mg is essentially 2 kgs. This means the X value, which is Mg over M total, is essentially 2 over 10, which is 0.2. So your X value is known to you. You have to determine the pressure in the tank and the volume of the tank. Since you're talking about 90 degrees centigrade isothermal line, you'll go to table A4. simply go to 90 degrees centigrade and read the corresponding pressure in front of it. This would give you the pressure of the tank. If you want to find the volume change of the tank, or the the volume of the tank, it is simple. You'll have to use the relationship V average, or V is essentially equal to Vf plus X Vfg. X is known to you. Vf for 90 degrees is known to you. Vfg can be calculated using Vg and Vf, the difference of the two. So you used Vf, X value, the difference of Vf and Vg, to find out the specific volume. Once you have the specific volume and the total mass of system is known to you, you'll just have to multiply to find out the volume of your system. Then comes the problem of superheated tables and interpolation. So you have to determine the temperature of water when the state is 0.5 megapascal and enthalpy is 2890. So the first thing is you have to identify the region. You'll go to 500 kilopascal or 0.5 megapascal line, compare the value of H with HF. It is greater, H is greater than HF, H is also greater than Hg. That means you are in the superheated region. So at 0.5 megapascal, the enthalpy is greater than Hg, so you are in the superheated region. You'll have to go to table A6 in order to find out the properties. In table A6, you'll go to 0.5 megapascal pressure and you will identify the enthalpy. If you look at the enthalpy column, you know that your enthalpy lies in between these two values, and you don't have the direct value of temperature for that enthalpy value, so you'll have to do the interpolation. In interpolation, you'll use the value of 200 degrees centigrade and the corresponding enthalpy, T unknown, which you have to find out for the enthalpy value of 2890, and a greater value which is 250 degrees centigrade, and the corresponding enthalpy value is known to you. So now you just have to take the difference between these two and these two on the left hand side. So you can take any two temperatures, the difference of any two temperatures and the corresponding enthalpies on the right hand side. Similarly, the difference of any two temperatures on the left hand side and their corresponding enthalpies. By any two temperatures, I mean any two temperatures. If you're using 250 over here, you will use the corresponding enthalpy on the same position, right hand side of the equality. Similarly, if you're using 200 over here, you will use the same enthalpy value on the right hand side of the equation. T, since you know the value is 2890, you can write the corresponding enthalpy, and for the 200 you're also familiar with the enthalpy. This would give you the temperature to be 216.3 degrees centigrade. You should remember that if your enthalpy value lies in between these two values, your temperature value should essentially be in between these two values. Moving on towards the compressed liquid data. In a compressed liquid state, water, which is at 80 degrees centigrade and 5 megapascal pressure, you have to find the internal energy using the compressed liquid table and using the saturated liquid data. Compressed liquid table, it is simple as you have table A7, you'll directly go to the pressure, which is 5 megapascal. For this megapascal pressure, you'll go to temperature, which is 80 degrees, and you will directly read the value of internal energy, which is 333.82 kilojoules per Kelvin. Then moving on, if you have to use the approximation, now approximation is that U is essentially approximated as UF at the saturation temperature. So your temperature is 80 degrees centigrade. You need to find out where do you have 80 degrees centigrade at the saturation temperature. So you'll go to table A5 that lists down the saturation temperatures, and if you see 80 degrees falls between 75 and 81, 75.86 and 81.32. So you'll use these two temperatures and the enthalpy value, internal energy values, to formulate your table. This is your table again. 75.86, 81.32, the corresponding enthalpies are written. 80 degrees, you have to find out the enthalpy, which is unknown. You just have to take the difference of temperatures on one side, temperatures on left hand side, enthalpies on right hand side, and solve it. This would give you the value of enthalpy, which again lies in between these two values, as the temperature lies in between 75.86 and 81.32 degrees centigrade. The last thing that we have to look into is essentially the piston cylinder device example, which is an example of double interpolation. In this example, the mass of the refrigerant is given and the initial temperature of the refrigerant minus 10 degrees centigrade is given. It is further said that the piston is free to move and has a mass of 12 kg, diameter of 25 centimeters, the atmospheric pressure is 88 kilopascal. It further says as the heat is transferred to the refrigerant, the final temperature of your system is 15 degrees centigrade. So initial and the final temperatures are given to you. You have to determine the final pressure as the first part. Final pressure would be the same as the initial pressure. Why? Because the piston is free to move and the pressure is basically contributed by the atmospheric pressure and the weight of the piston. So mpg is representing weight of piston divided by the cross-sectional area of the piston would give you the total pressure of your system, which is 90.4 kilopascal. So now you have two states. State 1 where your pressure is 90.4 kilopascal and your temperature is essentially minus 10 degrees centigrade, and state 2 where your pressure is essentially 90.4 kilopascal and temperature is 15 degrees centigrade. You have to find out the volume change of the cylinder and the enthalpy change of the cylinder as your system moves from state 1 to state 2. So basically you are looking into del V and del H for 1 to 2 states. For that you need to identify the regions, the region in which your state 1 and state 2 are lying. So the first thing is to find out the saturation temperature for the corresponding pressure of 90.4 kilopascal. You'll go to the table of pressure. You see 90 and 100 pressures are given. Corresponding saturation temperatures are given. You have to find out for 90.4 kilopascal the saturation temperature. Again, doing the interpolation between 90 and 100 for 90.4 kilopascal to find out the temperature or the saturation temperature. The saturation temperature comes out to be minus 28.56 at a pressure of 90.4 kilopascal. Now, if you remember the temperature specific volume plot, if you have this line as 90.4 kilopascal line, and this temperature is essentially minus 28.56, both your temperatures minus 10 degrees centigrade and 15 degrees centigrade, they are above this saturation temperature, so your system lies in the superheated region. This means that if your saturation temperature is this at 90.4 kilopascal, for state 1, since your temperature is minus 10 degrees centigrade, which is greater than saturation temperature, you are in the superheated vapor region. Similarly, for the second state, you are again in the superheated vapor table. So for the first state, you will go to the superheated table and identify the pressure. Now you have been given the pressure of 0.06 megapascal and 0.1 megapascal, but 0.094 megapascal is not given to you. So you have to interpolate. For 10 degrees centigrade, the specific volume for 0.06 and 0.1 megapascal are given. You have to interpolate and find out for 0.094. Similar is the case for enthalpy. Minus 10 degrees centigrade, 0.06 megapascal is given. Similarly, minus 10 degrees centigrade, 0.1 megapascal is given. You have to find out for the pressure which is in between these two pressures. So I have constructed a single table. Minus 10 degrees centigrade, 0.06 specific volume is given. 0.10 specific volume is given. 0.094 you have to find out the specific volume. Similar is the case for enthalpies. You have to find out the enthalpy also. So this is for specific volume interpolation. This side is pressure difference. This side is specific volume differences. Similarly, the enthalpy, this side is pressure differences. This side is enthalpy differences. And once you solve, you'll find out the properties of specific volume and enthalpy at state 1. Now moving on to state 2, again the pressure of 0.094 megapascal is not there, and your temperature for state 2 is 15 degrees centigrade. So if you look at the temperature lines, 15 degrees is also not given. So the first thing is you find out the specific volume and enthalpy values for 0.06 megapascal at 15 degrees centigrade by interpolating between 10 and 20. Similarly, you will do the interpolation for 0.10 megapascal and find out the values for 15 degrees centigrade specific volume and enthalpies. So for 0.06 megapascal, you'll need to find out the value for 15 degrees centigrade of internal energy, so specific volume and enthalpy, and so is for 0.10 megapascal. You will find out the values for 15 degrees centigrade, the specific volume and the enthalpies. Once you have the properties at 15 degrees centigrade for both the pressures 0.06 and 0.10, now you will interpolate and find out the value for 0.094 kilopascal. So your temperature is 15 degrees centigrade. For 0.06 and 0.010, you have found out using the interpolations these values. So now you'll do another interpolation and find out the value for 0.094, the specific volume and the enthalpy. These are the properties for state 2, 15 degrees centigrade and 0.094 megapascal. Now once you have both the properties for state 1 and the values for state 2, what you have to do is initially you need different specific volume as your system moves from state 1 to state 2, and you just multiply it with the mass given to you in the statement. This would give you the change in volume. Similarly, you'll find out the difference between the enthalpies as your system moves from state 1 to state 2 and multiplied with the corresponding mass. This would give you the change in energy as your system moves from state 1 to state 2. So this is a multiple interpolation problem where you have missing data in both the rows for the pressure and the column. This is how you do the multiple interpolations. So this brings us to the end of revision for property tables.